Welcome to this IMS pre-conference tutorial on mmWave radar applications in safety and disaster management applications. My name is Jan Barowski. I'm with the Institute of Microwave Systems at the Ruhr University of Bochum in Germany. And I'd like to thank the organizers of this pre-conference series for the opportunity to present our work here in this field. And I highly appreciate the opportunity to present our research to you. Our work in the field of safety and disaster management is strongly linked to the topic of mobile material characterization and localization. How does this come? Imagine, for example, a warehouse scenario in which, for whatever reason, there might be a critical situation. Within this scenario, an autonomous unit, whether it's a drone or some other robot agent, would be highly useful to collect relevant data about this scenario. For example, about the status of items inside or about persons in the need of help. The far goal of our long-term research project entitled Marie is to provide a dynamic material map, like you see here, that is available to emergency forces, for example. Let me briefly note that this project is funded by the German Research Foundation and is a collaboration of several German universities as well as Fraunhofer research institutes. Within this larger context, the indoor localization of the autonomous platform, the acquisition of data, and the characterization and identification of materials and objects or people inside can be done by mmWave and terahertz sensors, as they are, in contrast, for example, to optical cameras, very robust against harsh conditions like smoke or dust, for example. Additionally, wireless sensors operating in the very high frequency regimes above 100 GHz come with the advantage that they have very high bandwidth available, and therefore the resolution, for example in range, when you think of radar, are very high. Additionally, if you do imaging and spectroscopic analysis, you also benefit from the widely covered frequency range. Within this talk, I would like to set the focus on the topics of ranging and localization of this autonomous unit, which we have, for example, investigated on by using coded beacons that might be available in the environment and that can serve as landmarks. And in this context, of course, the coding is necessary to identify the current reference points. Furthermore, we have investigated on radar-based methods for material characterization, which have the potential to be very mobile in contrast to laboratory setups, for example. In this context, the characterization of the electromagnetic properties and the spatial mapping of these properties by imaging methods are key to the semantic identification of materials and objects, like, for example, these containers here, to provide this material map later on to some external forces. So in the remainder of this talk, I would like to take the opportunity to provide you some tutorial and fundamental background again to ultra-wideband mmWave frequency modulated continuous wave radar sensors and how they can be used as spectroscopic sensors. I will further explain our approach to radar-based material characterization, which is the basis for material identification in a semantic sense. I will give a quick overview on radar imaging techniques, specifically the synthetic aperture radar, and then show you some of our latest results in radar-based room exploration by a robot unit, and then finally give a short conclusion in the end. Let me start with a brief overview why FMCW radar-based sensors are so versatile in this context. Of course, ranging and the localization of targets are most fundamental in radar science, but especially ultra-wideband mmWave sensors allow ranging and precision down to a micrometer scale by advanced algorithms, which is very highly beneficial. Additionally, the wide frequency range allows to consider the radar as being very similar to a one-port vector network analyzer. And thus this enables us to do advanced measurements in dielectric characterization and the investigation on the spectroscopic analysis of materials under test. Furthermore, imaging techniques like synthetic aperture radar can be used to obtain images at almost optical quality, which is due to the short wavelengths in the millimeter wave and submillimeter wave regimes. Still, the signals are able to penetrate many materials, providing insight into the internal structures, which is also very useful for non-destructive testing, for example for modern lightweight fiber-reinforced materials. As this talk is intended to be of a tutorial nature, let me just give you a brief recap of what's going on in such a frequency-modulated continuous wave architecture. Let us start with this voltage-controlled oscillator here to the left, which creates an oscillating signal that is going to be transmitted later on. By applying a tuning voltage to this oscillator, we can linearly modulate the frequency. Thus, the transmitted signal looks like a chirp, right? It starts at quite a low oscillation frequency, which is increased during the signal duration. It passes the coupler or circulator that could be part of the front end and is radiated from an antenna, hits upon a target, and is reflected or scattered back to the radar front end. And thus, at that time, we have, due to the propagation distance between the antenna and the target, a time shift in the signal. In the radar front end, we have this circulator, for example, that now isolates the received signal and feeds it towards a mixing stage, which on the opposite side has the original transmit signal as an input. Thus, at each moment in time, this mixer basically downconverts the original linear frequency ramp and the received one, which is almost identical except for a small time shift. And thus, at the IF output of this mixer, we can do a low-pass filter to remove the high-frequency oscillation from the signal and obtain the low-frequency beat signal. And due to the linear frequency ramp, this beat signal frequency will be proportional to the distance between the sensor and the target. If we look at this on a more fundamental level, it's beneficial to separate the transmit and receive part for the sake of simplicity. The signal is radiated into free space, is affected by the propagation via an impulse response, and is received back into the receive antenna. So the measurement scenario is basically described by a linear time invariant LTI system, and what we want to measure is basically the impulse response, or in frequency domain the transfer function of our propagation environment. We can briefly go through all the mask parts. So basically we have our transmit signal here, which is a harmonic oscillation with a given instantaneous phase. This instantaneous phase is mainly described by the linear frequency modulation, so we can take the instantaneous phase as being integral of the instantaneous frequency. Thus, we obtain the transmit signal here. We see that we can describe the propagation environment for a single target for the sake of simplicity by a very simple impulse response function with the delta distribution here, accounting for the distance to the target. By convolving that with the transmitted signal, we obtain the received signal, which is basically almost identical again to the transmit signal, except for this time shift, which also affects the frequency modulation. We can now calculate the mixer output signal as the product of the transmitted and the received signal, and this over bar here indicates that we are only considered in the down-converted mixing product. So if we apply the mathematical rules for the products of sine and cosine, we see that we end up with this argument here. We can see that it's affected by the time delay to the target, that it has a linear frequency term and an additional term that's quadratically proportional to the distance to the target. And by assuming this, that the delay induced by the target, which is on the scale of nanoseconds in short-range scenarios, is much smaller than the pulse duration t, we can neglect this part. And now we can see that our received signal, the intermediate frequency signal or beat signal, again shows this linear frequency modulation as a function of time. And this is now highly interesting because we can describe this as a linear relationship between the instantaneous transmit frequency and the sampling time of the ADC. And this basically means that we can exchange the sampling time of the intermediate frequency signal basically with the instantaneous transmit frequency axis, and thus consider this as a frequency domain measurement of the transfer function of our original propagation environment here. So if we now look at an actually done measurement, we can utilize this linear relationship between frequency and sampling time and replace our ADC sampling time axis here, which has been a few milliseconds, by an axis of instantaneous transmit frequency. And in this case, we had an ultra-wideband sensor used between 68 GHz and 93 GHz. And our IF signal here basically corresponds to the real part of our propagation environment's transfer function. And if we look at it this way, it's quite natural that we can do the Fourier transform by a fast Fourier transform approach, for example, to obtain the radar echo, which is then equivalent to the impulse response of our propagation environment. And of course, the axes in both domains are strongly linked. The angular bandwidth, the frequency spectrum that we can cover with our sensor, determines the range resolution in the radar echo or in the impulse response, and the frequency step size, which is proportional to the sampling rate of our ADC, determines our unambiguous range in the echo domain, which is important for us if we want to look at targets that are very remote to the sensor. So how does this help us in our localization problem? If we again consider our autonomous robot, we want to localize it by the usage of passive beacons or landmarks in our environment. And in order to distinguish these landmarks, they need to be coded somehow. And for that purpose, we investigated together with our partners on frequency-coded dielectric resonators. So for this purpose, we investigated on dielectric resonators made from zirconium oxide, which are basically spherical particles that can be excitated in their TE101 mode, for example by a mmWave, which is impinging on an array of these resonators. And if we look at the array itself, we can see that at the frequency of resonance, approximately 85 GHz, we get a strong reflection. Otherwise, the reflection is quite low. This may be not that feasible if we want to have these as landmark beacons, because then it's nice to have a large RCS over the total considered frequency range. So we extended this with a metal plate in the back, being a half a wavelength away. So outside of the resonance region, we have the strong reflection from the metal plate. And at the frequency of resonance, we get a notch because the transmissive array is now causing an interference. So since our landmark beacons should have quite a large angle of acceptance, meaning that we would like to have a large RCS over a wide angular range, we integrated an array of these spherical resonators into a dihedral. So one side of the corner reflector is now covered with this resonator array, and you can see the photograph here with some adhesive tape that carries the spherical particles here. And we investigated on the reflection properties with our frequency modulated continuous wave radar system again, which we calibrated beforehand. And we can see that if we compare to a conventional dihedral, which is the blue curve here, we get quite a similar shape with our proposed one. So the angular acceptance angle is a little bit smaller, and the RCS is only a little bit less, but still quite sufficient for our purpose. And then we identified on extracting this spectral response that we would like to use to identify the current landmark over a large distance range. So in this plot you can see now the distance to the target ranging from 0 to 5 meters, and on the x-axis the frequency of the FMCW system. And we can see that here at approximately 85 gigahertz again, we have one constant line where the RCS drops at the specific frequency, which can be used to identify now this landmark. And if we would have used particles at larger size or different permittivity, this frequency of resonance would have shifted somehow horizontally here to code another beacon. So this topic of spectral identification brings me to our next topic, the topic of radar-based material characterization. And for this purpose, I would like to present to you a quasi-optical radar setup operating from 200 to 250 gigahertz here in this cage system. So we have here our silicon germanium based FMCW radar with this chip here at its heart. From this chip it radiates by two on-chip antennas into this elliptic lens antenna, which provides a collimated beam. And here in this lens holder again, there's a planar convex lens to focus this collimated beam again into this aperture here, where we can place the material under test. We can do a simulation of this setup at 240 gigahertz, and we can see the spherical radiation within the lens. The collimation of the beam is not that clearly visible because the next lens is quite close to it, but we can then see that the beam is nicely focused into this aperture plane here, where we get a spot size of approximately 6 millimeter diameter. If we now look at measurement results obtained from this system, we can investigate on it based on the radar echo, for example. So we see there are several reflections inside our target area. Here, very close to the system at zero distance, we have the reflections from the on-chip antenna, the reflection from the elliptic lens, the second lens reflection from the additional planar convex lens, and here at 0.6 meters approximately, we have the reflection from our target within the aperture plane on the right-hand side of the setup that I've shown before. And then there are additional reflections as well. So what we now do is we want to extract especially this pulse here at 0.6 meters, since this carries our spectral information on the target. Additionally, this pulse is impacted by the system-specific errors, which are like additive errors from all these lens reflections, and of course also have multiple reflections somehow beneath this power level here that might nevertheless disturb the system. And we can see that we have some distinct pulse shape here that we also want to correct for. So in the first step, we do a background subtraction by measuring into empty space. By this we can remove all these antenna reflections here, because these are constant throughout all measurements and are visible even without a target in the aperture plane. And then we do a reference pulse measurement here in this red curve on a metallic target. And you can see here as well, there are no antenna reflections anymore because these are still constant. But you can see that even though we expect a nice single peak from our metallic target, we have like this double peak shape here, which is due to the system-specific pulse shape that is also affected by the lenses, for example, but also by the output power of the sensor and its flatness over the covered frequency range. So there are many components impacting this pulse shape. If we now want to correct for this, we do again a time gating on this area, for example from 0.5 to 0.7 meters, and transform the signal components here back into the IF signal domain, which we can consider the frequency domain again, as I've showed before. If we do so, we can look at the complex envelope, then, which is the red curve here, which follows nicely the raw measurement signal envelope that we've obtained initially. By time gating specifically to our target, we force all other regions in the radar echo to 0, and therefore we implicitly do a Hilbert transform, and this is the reason why we are now looking at the magnitude of the complex envelope here in this red curve. We can also look at this in a logarithmic scale now, being that we basically see now the reflection coefficient of our target as a function of frequency. We see that since we have a material sample of finite thickness, there's a Fabry-Perot resonance here, which is basically results from the reflection at the front side and the interfering reflection from the back side of the material sample. So this is our measurement result now, and in the next step we would like to identify the material parameters from the sample. And therefore we do an optimization, so we can analytically describe this, the reflection coefficient of a dielectric slab, and we can use some starting relative permittivity here as an initial guess. And we now want, by iteratively optimizing, to minimize the difference between our red model curve and our blue measured curve. So this is our first guess, which is not that bad, but also not very good at all. So we can do a first iteration based on a Gauss-Newton approach, for example. So then we see that our model now improves, so the difference becomes less, especially the depth of the resonance is reduced by introducing some losses to the material, by increasing the imaginary part of the complex relative permittivity. So this basically determines the Q factor of this resonance. So now we get this a little bit matched better. If we do a next iteration, we can see that we now can shift the frequency of resonance by changing the real part of the relative permittivity, and this is due to the fact that the real part basically determines the wavelengths within the material, and if we increase this, the material becomes electrically thicker, so that the frequency of resonance moves to lower frequencies. So now that we have characterized our material and have the ability to localize ourselves within the room, I would like to give a very brief introduction into radar imaging, specifically radar imaging by synthetic aperture radar, which will be necessary for our next step, then the radar-based room exploration. So if we would like to do imaging by an electromagnetic system, we can, for example, do a focal plane imaging by radiation from a tailored aperture, like we did basically before. So we use a lens or several lenses to create a focused beam that provides a high lateral resolution, so in this case resolution in Y direction here, from the beam pattern. The resolution in range direction, so in this case on the x-axis, is still determined by the bandwidth of the sensor. So this is beneficial in some applications where we're pretty sure about the position of our target. But if we would like to cover a wide range here on the x-axis with a focal area, it's beneficial to use focusing algorithms, especially the synthetic aperture radar approach, or SAR, is beneficial for this. This is basically based on a measurement in a plane or a 1D aperture, where we use an unfocused antenna to widely illuminate our target. And since we do a coherent measurement. We can utilize the phase relations from our reflected pulses and correlate them against the point spread function of our aperture, and this basically provides us a focused image. So I'd like to explain this a little bit more in detail now. So for the synthetic aperture radar method, we would like to consider now a simple 1D scan of our radar sensor along the y-axis. So the sensor is moving along this axis. The x-axis corresponds to the range of the system. So we get 3 radar echoes here now from 3 point targets located in our environment. And we can see that here at the point of closest proximity, we expect the target to be positioned. What we also see, of course, is our radar sensor has no angular resolution, but only range resolution. And this is now what we would like to improve by coherently processing the complete data set. The algorithm we use for this purpose, in this case, is the back projection, which is very flexible, not the most efficient one, but very straightforward to understand. So if we consider our first measurement here at position 0, we basically get a range profile on the y-axis, and we can see that we have our 3 target reflections here, and the correlation in time domain can now basically be interpreted as interpolation of this radar echo onto a Cartesian grid, where we calculate the radial distance to our sensor point and interpolate with the point in the radar echo. So basically these target reflections now appear as circles in our interpolation, and the red circles here indicate the original positions of our targets. So if we now do this for, let's say, 3 positions, we can see that we get constructive interference at the points where the targets are located. But of course there are many disturbances still in the image. But if we now do this for, let's say, more than 1,000 samples, we can see that the targets are nicely focused, because the reflection phases only match at the positions of the targets and otherwise cause random or destructive interference. So this provides us 3 nicely resolved point targets. So this can be implemented, for example, on a lightweight 3D printer, mechanical platforms, where we have the radar sensor mounted here, where the print head is usually located, looking downwards onto different material samples here that are to be investigated. What I would like to highlight here regarding the implementation is that basically we obtain this range profile map from the sensor itself after Fourier transforming the raw IF signals. And the back projection algorithm is now especially feasible to be implemented on a graphics processing unit due to its parallel architecture. This is especially due to this interpolation and coherent integration step that we do in the algorithm, that only that each pixel in the output image only has reading access to this raw data map here, and there is no need for a data exchange between this pixel, for example, and its neighbor. So we can basically arrange this data map here to fit the computation units on our GPU, so that each core on the GPU integrates for 1 pixel in the image, and this can be done very efficiently. So now that we are able to focus targets in arbitrary distances, we can utilize this in our radar-based room exploration, where we have targets in several meters distance in parallel to targets very close to the sensor. For this purpose, we would like to do SAR imaging by measurements of a radar sensor that is mounted on a robotic arm. In our case, we considered a radar sensor here operating from 68 to 92 gigahertz again. And the SAR geometry we utilize here is called an arc synthetic aperture radar, which is basically shown here. So we have a circular movement of our synthetic of our radar antenna. That this arc now spans the synthetic aperture. We have a point target looking outward, and this circular movement now basically affects the resolution of our target. This is very similar to a circular SAR that I mentioned here for sake of completeness, but in circular SAR the antenna is looking inward and all the time focuses basically onto a target, which can then be imaged at a very high resolution, since the whole circle is covered in most applications. Again, in our case, the antenna is looking outward, so its edge case for a circle with infinitely large radius, which would be again the linear aperture. So here in this image you can see the robotic arm that we are using. The most simple movement is basically a rotation of the fundamental joint here at its base, and the radar sensor is looking outward all the time. This provides a radius of our circular movement of 60 centimeters, and you can see the synthetic aperture radar image here on the bottom of the slide, where we can see, for example, the corner reflector that we're looking at here as a reference target quite close to the sensor, but we can also identify the rectangular room shape of our laboratory environment here. We can see several targets which are quite nicely resolved. This is a monitor here, for example, and we can also see some targets that are still quite blurry, and this, for example, in here is the corner of the room, and not only the let's say dihedral corner at the height level of the sensor, but also the lower trihedral that is created from the ceiling or the ground. And since this is these targets are below or above our circular movement, these can still appear here as blurred out targets, because the SAR processor only operates well in this height plane. So this basically provides us now a quite nicely resolved image of our room. If we now want to do room exploration, of course, we would like to have a moving robot within our room. So we do several measurements from different locations. And in the first step, we considered 3 individual movements here, for example, and want to do a simultaneous localization and mapping approach, a so-called SLAM approach here, to register all the different radar images with each other to update a map of the room. So for now, we will only like to consider the more simple case that we do a complete SAR image stationary at each of these positions. So while the SAR image is taken here from position 1, for example, the robot itself is not moving except on the circular trajectory, of course. This provides us with the first image. Then we move the robot, and also we might rotate it a bit. This provides us the second image, where we can see a similar room shape, but we see the translation of the image. We can also see that the images are rotated against each other, and we also did this for third iteration. And then by correlating in the dimensions of translation and rotation, we can provide an updated map that incorporates all 3 measurements, and we can also see that the resolution of the overall image is additionally improved. So we get a really nice image of our laboratory here with the rectangular walls, with our shelves at the walls, and with different objects within the room. So of course, in a real world scenario, especially in an emergency scenario, there's not always the time to do these stationary synthetic aperture scans on the circular trajectory before moving the whole robot platform. So what we now assumed was that we have a superimposing linear movement of our center of rotation. So the robot is somehow moving within our scenario while it scans the room on a still circular track with its antenna. So we end up with this red spiral trajectory of our antenna. And in our approach now, we wanted to identify this linear movement component from these SAR images, since it might not be known that precise beforehand. So what we basically did was we divided our complete movement into several small sub-apertures, and each sub-aperture is only a few degree large, so we can still assume that we have a circular movement for this region. We calculate the synthetic aperture image of this part of our complete data set, and we see that the resolution is not that good. We see that it does not cover the whole room, but this we considered our starting point. And then we cannot be sure if we follow this trajectory or this one here. So we calculate the SAR images for a bunch of different movements of our robot foot point. And for each of these hypothetical movements, we create the SAR images and we correlate these against our original one, and we assume that the SAR image having the highest correlation fits best to the actual movement track of our robot. And by this, we estimate the superimposing movement, and we can see that this works very, very well if we take if we consider the complete trajectory of our system here. So in red, the curve shows the ground truth, which we commanded our robot to move while scanning, and the blue curve is the estimated movement that we obtained from the correlation of several synthetic aperture images having each only a few degree size in our scenario. So if we now take this estimated movement as the trajectory for our antenna, we can do the global SAR image again, which provides a more highly resolved image of the room, and we can still see this nice rectangular shape here, and we see that there are our several targets within the rooms and our shelves here, for example, which were on the left-hand side beforehand. Okay, so this brings me to my summary of this talk. I showed you the scenario of the acquisition of material maps that we would like to provide to emergency forces in safety and disaster management scenarios. For example, if you consider the introductory scenario with this hall. I focus especially on the robust localization, imaging, and material characterization by silicon germanium ultra-wideband radar sensors, which is basically related to our work on the frequency domain analysis of the frequency modulated continuous waveform, especially for ultra-wideband sensors. Of course, if you would like to really identify a material and not only determine its dielectric properties, you need to do like a semantic additional identification step, and this can be, of course, further improved if you use complementary photonic systems that cover several terahertz of bandwidth that provide you a huge spectral information with absorption lines, for example, on the material that you currently consider. I'd like to mention again that the whole project is entitled Marie, which is a collaborative research center funded by the German Research Foundation, which is a consortium of several partners throughout Germany, focusing on terahertz and millimeter wave measurements in this kind of scenarios. I'd like to thank again the organizers of the IMS for inviting me to this talk, and I hope you enjoyed it. Thank you.